Okay, so today we are going to continue with our lessons from where we left off. So last meeting we discussed about how to determine an increasing and decreasing function without graphing. Okay, visually if you graph, you will be able to determine if you have an increasing or decreasing function. Okay, wait a bit, yeah. Why can't I change it there? Okay, so if, for example, we have something like this, okay, if it's going this way and you have a point somewhere over here, you will know if it is an increasing or decreasing function using number one, using test points. Test points, meaning if you test this, if let's say this is now x and you compare it to a point somewhere here, it's like like testing a limit. Okay, if you will now get a point somewhere here, okay, and then get another point somewhere here and test values. This is now your test points, these blue things over here. Okay, using these two test points and you compare it. If you will now have here x is increasing, okay, so greater than 0 and then greater than 0 again. So that is now going to be an increasing function, okay? If it goes the opposite direction, so let's say we have something like this, and this test point and this test point, if you compare and you said x is lesser than 0, and here is also x lesser than 0, so it's going down. So that means now that this is a decreasing function. Okay? You can find this in, instead of graphing, okay, instead of graphing, as we said, you can test it if it is an increasing function or decreasing function using your first derivative. Okay, you can find the definition of the first derivative test in your textbook. Okay, what page is that? On page 50. Okay, if f prime is greater than 0 for all values of the interval, then it is now going to be an increasing function. And if you look at y prime again, okay, or f of x prime, and if it is now lesser than 0 in a certain interval, then it is a decreasing function. Okay, so increasing and decreasing function. So how do we use this idea now in graphing? Okay, so we have that idea. We can test the point. If it is now going to be going up and steadily going up, then that's an increasing function. If it goes down, then it's a decreasing function. Now, we can describe the movement now of a point without even graphing. But to complete our idea, we still need to understand what is the behavior of the points in a certain graph of a function. So your maximum or your increasing and decreasing function can be used to analyze a certain graph. For example, we have here a cubic function, and we know that sometimes a cubic function goes up like this, and then goes down, and then goes up again. Okay, so given this, given this x-intercepts, okay, x-intercepts, and then we also have here the y-intercept. Visual confirmation of it will tell us that this is decreasing, and this is decreasing again, and then suddenly this is increasing, this is increasing. That is very easy for us to determine because we can see the graph. We can determine if it is now increasing or decreasing. Okay? So, problem there is, what if you do not have a graph? how will you know if it is an increasing function at this point or it is a decreasing function at this particular point or interval? Okay. So furthermore, aside from this, we also learned that in a graph, there are parts of the graph that we call your stationary points. Again, what are stationary points? Stationary points
Point
are now, okay, continue.
point in the graph of the function where f(x) equals to 0, right?
Okay, so f prime of x is equal to 0 or the gradient of the tangent is 0, wherein we graph as one set of stationary points, wherein this are now called your turning points. Okay, your turning point is a point wherein the behavior of the graph changes from increasing towards decreasing. Okay, if you check to the left of this stationary point, okay, and it is increasing, and then check to the right of this stationary point and it becomes decreasing, okay, then this is now called a maxima. This one clear? This is now a turning point, particularly a maxima. Now, the other turning point is called a minima. If you check the left side of this turning point, if it is now decreasing using your first derivative test, if it is now this point is decreasing, and then this point becomes increasing. And so there's a change from decreasing to increasing. So that is now one type of stationary point. Okay? This is now called number one, your turning point. Turning point. And that is now a maxima, and a minima. Okay. However, there's another type of turning point, and this turning point is now called a point of inflection. Okay? There are times wherein the graph looks something like this. Okay? Wherein it becomes steady enough, but then continue going up. Okay, so there's a pause. So if you try to check the gradient wherein m equal to 0, because this is a horizontal line, the gradient of the tangent at this particular point, okay, at this particular part of the graph, m is equal to 0. However, the behavior of the graph is different from being a maxima or a minima. Why? Because if you check the left side of this point, the graph is increasing. Okay? It's an increasing function. And then to become a minima, it must decrease. It must go down, supposed to be. Okay. However, the graph did not go down. The graph, when we check at the right side of this function, if we check it, it went up. So increasing and suddenly continue on increasing. Okay. So when you use your first derivative test and you see this behavior of the graph from this point, from the left side and the right side of this point, then you will say that it is not a turning point. However, it is now called a point of inflection. Okay? So these are now the things that we need to apply in order for us to be able to understand the movement of points in a certain function. Okay, so before we move on, is this clear?
Yes, it's clear.
Is this clear? Yes. Okay. Now, let's try to apply this knowledge that we have in graphing higher order polynomials. Okay? So, when we were in lower levels, it's easy for us to graph quadratics. Okay? For quadratic equations, what are the things that we need to find? We just need points. Okay, your y-intercept or x-intercept. Okay, once you find your x-intercept, the next thing that you need to find is now your vertex, or in another name for the vertex is actually a turning point. So, and then you just connect it, x-intercept, y-intercept, vertex or turning point, and then go down. Okay, and done. You have a parabola. But when you are dealing with higher order polynomials, or say y equal to x cubed, okay, let me just get a problem, minus 3x squared, is that? Minus 3x squared minus 6x minus 6x plus 8. Okay, so this is cubic. It can, if I will give you raised to 5 or raised to 6, then that's the process is still the same. You still need to find your x-intercepts and your turning points over here. The only difference is the number of times that you, okay, meet the x-axis, okay, is higher. This one is x squared, so it touches the x-axis 2 times, okay, or it crosses the x-axis 2 times. If you have x cubed, then you expect that the graph touches the x-axis 3 times. It can go up like this, down, and then up, or the other way around, or it can go down, up, down, up. However, the parts are still the same. It will have the x-intercepts, will still have the y-intercept over here, then we still have our, what's this, maxima, minima, or if it goes like that, there is now again a point of inflection over there. Okay, so if you're able to determine these points, then you will be able to graph a certain polynomial. Is this one clear? Or that is our goal? Is this one clear?
Yes.
Okay, so this is now my challenge. Given y equal to x cubed minus 3x squared minus 6x plus 8, let's try to draw the graph of this based on the information that we have. Okay? So, procedures for graphing, we always start with the, okay, let's put a title. Graphing higher order. We have here y equal to x cubed minus 3x squared minus 6x plus 8. Okay, let's start with the easiest one. Y-intercept, let x equal to 0. Okay, can you do this? Then y equal to 0, 0, 0, y equal to, okay. So what we have, point at 0, 8. Next is x-intercept. X-intercept, let y equal to 0. So if this one becomes 0, we are left with x cubed minus 3x squared minus 6x plus 8 equal to 0. So how do we solve this? We can solve this by finding
synthetic division.
Okay, we can now simplify it and break it down to factors or find the values of x using synthetic division. Okay, good. So using synthetic division here, we can now get what? I hope that the rest can follow, yeah? As I said to you before, never forget your past lessons because you will be using it over and over again. Okay, using synthetic division, we will now have 1, negative 3, negative 6, and we have 8, and factors. Like what do we have? 1, 1, negative 2. This is going to be
Negative 2,
negative
negative
2,
8, and then after that 0.
negative 8.
Yeah, negative 8, 0. So the
Negative 8
x
and 0.
minus 1.
We have here our first, yeah, x minus 1, or the value of x is equal to 1. Right?
Yeah, I think so. Is that how we use synthetic?
Huh? Yeah. And okay, maybe you got, I was too fast. Okay, so this one is, we have here x minus 1 is our factor. Right?
Yes, teacher.
Yes? Okay. So this one now can be written in a quadratic form, which is now x squared minus 2x minus 8 equal to 0. Okay, so what factors can I bring out here?
Negative 4 and positive 2.
Okay, so basically this in factor form is made up of x minus 1, x minus 4, and x plus equal to 0. So what do you do? After this, you find values of x. This time, instead of cutting it into 2, you have cutting it into 3. X minus 1 equal to 0, x minus 4 equal to 0, and x plus 2 equal to 0. So x is equal to 1, x equal to positive 4, and x equal to negative 2. Okay, you understand this?
Yes, teacher.
Yes.
Yes. Okay. So now this is our x-intercept. In the x-intercept, you now have what? 1, 0, 4, 0, and negative 2, 0. Okay, so we already have several points. 0, 8, and 1, 0, 4, 0, and negative 2, 0. The question now here is, what will be the behavior of the graph after finding these points? Okay. Basically, we got something like this, right?
Yes.
Negative 2, somewhere in the negative. Yeah. Have here 1 over here, and then we have 4 over there. Okay, at least this one depicts our graph a bit. Okay, it's also going 0, 8. So if that is 8, okay, so we're almost there. So we have a basic shape like this. Okay, but the question now here is, where will be our turning point? How do we find this? And how do we find this? Okay, we now use your first derivative. Okay, you get your first derivative and then equate it to the gradient is equal to 0. So from y prime, you now get your, or from y, you now get your y prime or your first derivative. Okay, using your first derivative, what will we get?
3x minus 6x squared minus 6.
3x minus
3x squared.
6x squared minus,
No, teacher.
Wait,
3x
square?
squared minus 6x.
3x squared minus 6x minus 6. Okay, so that is now your first derivative. Okay, and then we just need to evaluate it somehow. Okay, so how do we treat? We have your first derivative, you can start testing. Okay, you can start testing using your first derivative test. This is at -1, correct? Is that -1? Sorry, at -2. Okay, you test at -1, just like testing your limit. Okay, just like testing your limit. If this is -1, if this is now -1, it's here. You test a small value here, let's say from here, and then test a small value here, and then look at the behavior. If it is positive and positive, then that means it's increasing according to our first derivative test. This is now on page 50. If it is increasing, or if the x value is, or f, if f prime is greater than 0, then it is now increasing. If we know that, then that means our graph is going up. If it is minus and minus, then that means it is now going down. Understand? So what values can we use at -2? We can use -2.1 maybe, just that is now somewhere to the left, and then use 1.9 somewhere to the right, and then just see if the values are like this. Okay, that's one way to test. Okay, however, since we are graphing, I would like to go straight turning points. Okay, so I will now let y prime equal to 0. Okay, that's what I'm going to test. When y prime is equal to 0, what are the values of x? Okay, please. So we will now have here 3x squared minus 6x minus 6 is equal to 0. Y prime is 0, so that means it's either it will be a turning point. Okay, we are looking for stationary points. This is now look for stationary points. What do you get?
Uh,
We can use
we can use the quadratic formula for this one.
Quadratic formula, yes. Quadratic formula. This one, use quadratic formula. Okay, give me x1.
I got 1 plus a root of 3.
Give me the decimal value. So you separate
Oh,
it
okay.
as x1 and x2.
2.73.
Positive 2.73, and the other one will give me most probably
Negative
a negative
0.73.
0.73. Okay, so which means now that I have 2 points in x that will give me either a 2 stationary points. And to find the exact location of this, you substitute in equation each one to find y. Okay, substitute in the equation to be able to find the values of y.
Y1 would be negative 0.0213.
Okay, y1 will be
Negative
negative
0.0213.
in
Yeah.
not in y prime, substitute in y, this one, the original.
Oh, okay. Wait, picture.
Here, substitute here.
I got negative 10.39.
10.39, while y2, when you substitute this,
Positive 10.39.
will give you,
Positive 10.39.
okay, so just got lucky, okay. It can happen that it will have the same value, one in positive, one in negative, but sometimes these are two different values. Okay, so with that, it completes our points that we need. We have now two values. We have here 2.73 and negative 10.39. That's one of our stationary points. Another one is negative 0.73 and positive 10.39. Okay, if we put everything together, how will it look like? So we start off with our y-intercept, which is now 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 exact. Okay, so there. We have our x-intercepts to be at 1, 0. Okay, there. 2, 3, 4, 0. And then negative 2. That is now our intercept. Okay, so the behavior of graph over here, we did not check. We did not check using your first derivative test, but we can. Okay, we can do that later. However, we went directly to your turning point. At 2.73, somewhere near here, that's 2.73 is here. It is now negative 10.39. So 1, so it goes down. Okay, that's good because of that. So I'm just using that as a marker. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10.39 is somewhere there. Okay? One, it's at negative 0.73. Negative 0.73 is somewhere here, and it goes up. Okay? And this is now 1. This is 8, 9, and 10, so it goes higher there. Okay, so can you imagine what happens there? These are now your tangent points wherein the gradient is 0. So can you imagine the shape of the graph? You can test here if you want. What will be the value of the graph down here at -2 or -3? Okay, but I'm guessing since that's a turning point, it will need to go up. Yeah, it will need to go up, touch this point, turn, cross the y-axis, touch this point, and then continue going down, reach this turning point again over here, and then go back up, then there. Since it's cubic function, it continues on. Okay, so this is now the most accurate graph that you can draw using now with the help of your first derivative test over here. This one clear?
Yes.
Yes.
Sure. So the stationary point is
question?
kind of like the vertex, is it?
Hmm?
So the stationary point
Sorry,
kind of
yes.
acts like.
Yes. The stationary point again is two types. One is a turning point. Well, if it is if you want to relate it to quadratic, then this one can be your vertex, maxima, minima.
Okay, teacher.
Okay. However, my question here is without graphing, is there a way for us to determine if it is a maxima or a minima? So that's the question that we need to answer by next meeting. This one, we see it, we visually confirm it, that it turns up here, and because the pattern is that's a higher point than the, what's this? Y-intercept, it needs to turn here before it can go down, right? So logically, we reason out that the graph must be going up there, turn, go down, get these 2 points, turn again, and then go up. That's how we logically explain this. But what if we are not graphing and we just see this point and this point? Is there a way for us to determine if it is a maximum point or a minimum point? Okay, so with that question, I'm going to leave it for you to think about it, and we will discuss it by next meeting. Okay, so but this one is going to come out during the test, how to graph higher order polynomials. If I'm going to give you raised to 4 or raised to 5, then you should know how to trace. Okay.
Okay, teacher.
Okay, teacher.
Okay, so that is it then. Goodbye.
Thank you, teacher.
Goodbye and thank you.